So when we apply the force here at a 45-degree angle, notice the trajectory of the cylinder. The kinetic energy is maximized at this point.
Item 1. You are part of a multidisciplinary engineering team working on a major project that involves designing both a high-precision laboratory weighing scale and the structural support system for the facility where the equipment will be installed. The laboratory will be used for advanced scientific research. So both the weighing instrument and the building's structural elements must be extremely accurate and reliable. As the design engineer responsible for verification and safety, you must ensure that the formulas used in both the weighing scale design and the bridge-like structural support beams of the laboratory are dimensionally consistent before prototypes and construction begin. Dimensional errors at either stage could result in equipment malfunction, faulty measurements, or structural instability. Task A. Identify the fundamental and derived physical quantities required in the calibration of the weighing scale. Use dimensional analysis to check whether the force acting on the mass, F equals mg, used in the scale design are dimensionally consistent. Explain why dimensional analysis is crucial in verifying these equations before building the prototype and the structural support system for the facility. Discuss potential problems if an incorrect formula is used and how to resolve them. Fundamental physical quantities. These are the base quantities needed because the weighing scale relies on mechanical and sometimes electronic measurements. Mass, m, the main quantity being measured. Length, L, used in measuring deflection, spring extension, lever arm length, or oscillation length. Time, T, required when calibrating using oscillation period, e.g., in balance or spring systems. Electric current, I, only if the scale uses electronic sensors like strain gauges or load cells. Derived physical quantities. These quantities come from combinations of the fundamental units and are essential for calculations and calibration. Acceleration due to gravity, G, used to convert force to mass. Period. Of oscillation, T, used in dynamic calibration of balances. Voltage resistance, electrical output from sensors in digital scales. Pressure stress, if sensors use strain gauges, used for electrical load cell deformation. Use dimensional analysis to check whether the force acting on the mass, F equals mg, used in the scale design, are dimensionally consistent. F equals mg. Left-hand side, force F has the SI unit Newton. Dimensions of force equals mLt power -2. Right-hand side, mass m, dimensions of mass equals m. Acceleration due to gravity, g. Dimensions of acceleration due to gravity equals Lt power, multiplying dimensions of mass times dimensions of acceleration due to gravity equals m times Lt power equals m Lt power. Left-hand side equal right-hand side. Therefore, the equation F equals mg is dimensionally consistent. Explain why dimensional analysis is crucial in verifying these equations before building the prototype and the structural support system for the facility. Saves time and money by identifying mistakes before manufacturing. Ensures loads, forces, and safety factors obey physical laws. Prevents unit errors that could lead to faulty calibration. helps detect missing or incorrect physical parameters early. Ensures formulas used can predict real stresses in beams and supports. Discuss potential problems if an incorrect formula is used and how to resolve them. Possible challenges: incorrect sensor dimensions, wrong readings. Wrong calculation of spring extension or lever arm, inaccurate mass measurement. Choosing a sensor outside the required force range. Corrections: use SI units consistently. Perform periodic calibration using reference masses. Include tolerance analysis in design. Use software unit checking tools. Measure actual manufactured dimensions and adjust calibration constants. Item 2. You have been invited at a military camp in DR Congo for a science show connected to the launching of rockets. Unfortunately, an ambush has been made to the camp, and the commander-in-chief of the camp has been shot dead, and so you are left alone with your fellow learners, because other soldiers have ran to attack the enemy before they reach the camp. As you are still looking for where to hide, information from the radio call has come that a rebel, who is located at a distant cliff of height 60 meters, is launching a missile towards the camp at an approximated angle of elevation 30 degrees, with a velocity of 20 meters per second. And so if the camp is to be saved from its impact, an interceptor should be projected at the same time with the missile from the campground at an angle of 30 degrees towards the missile so that they collide at a height of 60 meters above the ground, so that the field soldiers are not affected by the blast of the impact. Task: using your knowledge of physics. A. At which velocity should the interceptor be projected towards the missile so as to save the camp from the likely danger? You should guide the backup on the estimated horizontal distance of the cliff on which the rebel is located from the camp so that he can be taken down. At which velocity should the interceptor be projected towards the missile so as to save the camp from the likely danger? If both the missile and the interceptor are projected at the same time, by the time they collide, they will have taken the same time of travel. Let the initial speed of interceptor be u. Therefore, considering the motion of the rocket, projected will have covered a horizontal distance equivalent to range r. So the time it takes, time is equal to 2u sine theta over g. So time is equal to 2 times 20 sine 30 degree over 9.81. Time is equal to 2.04 seconds. This is the same time taken by the interceptor to collide with the rocket. So knowing the angle of projection and height above the ground at which they collide, the speed u of projection can be got from y equals ut sine theta minus half gt squared, where t equals 2.04 seconds. 60 is equal to u 2.04 seconds sine 30 degree minus a half times 9.81 times 2.04 seconds squared. 60 is equal to 1.02 u minus 20.41. 1.02 u is 60 plus 20.41. U equals 78.84 meters per second. So the interceptor has to be projected at 78.84 meters per second. B. Guide the backup on the estimated horizontal distance of the cliff on which the rebel is located from the camp, so that he can be taken down. Horizontal distance required from the sketch diagram above is the sum of r and x, r plus x, where range equal u squared sine 2 theta over g. Range equals 20 squared sine 230 over 9.81. Range is 35.31 meters. While x equals ut cos theta for the interceptor. x equals 78.84 times cos 30. X equals 139.29 meters. Therefore, the horizontal distance between the rebel and the camp equals this. 35.31 plus 139.29 equals 174.6. Thank you for watching. We meet in set 2. Please subscribe.